Okay, in section 2.5, we deal with Cartesian vectors in 3-space, and we're going to start out by just mentioning that here in the US we usually use the right-hand rule. So that involves a thumb, and here's a curled fingers, 1, 2, and a big fat one down at the bottom. So this is like a hand representation, cartoony hand. And the way this works is, so we're going to define y in this direction. We'll define z in the direction of the thumb. And then sometimes you can point a finger this way, or just know that x comes out this way. So what's interesting about this is you curl your hand around in a counterclockwise fashion, and that will also be positive for us to do. So this is positive z, positive y this direction, and positive x in this direction. And it's just a convention. If you live in Russia, I think you do it the opposite. You use left hand. But continuing on. So using rectangular components of vectors, well, using vectors in 3-space and rectangular components of vectors, it's really useful. I guess I should say using vectors in 3-space is really useful, because the trigonometry can get quite hairy. So first we're going to look at the rectangular components of a vector. So for a vector, say vector A coming out here in 3-space, so this is a 3-dimensional vector. It's going to have x, y, and z components. Maybe we'll call this vector vector A. So vector A is made up of 3 mutually perpendicular components. You're going to have an AX component, which will, let's do these in green, come down this. AX component. AY will head off into this direction. So right now, AY, right now, we have gone first in the x direction, and now essentially we're heading in the y direction to this point. It's going to be parallel to the x-axis where we come out here in the y direction. So we go the x direction, the y direction out here, and then up in the z direction. We haven't gone far enough in the y direction, it looks like. Let me fix that up. Okay, and then we head up in the z direction. So here we go up into the z direction. So this is AZ. And you can think of this as though we actually follow these mutually perpendicular paths. So we've got the AY. So first the AX, then the AY, and now the AZ. And that ends up in our resulting vector. So A is the sum of AX, AY, and AZ, as drawn here. We can find the magnitude of this A vector. And actually, before we do that, let us look at breaking this down into constant coefficient times a unit vector. So we could say then that A equals the magnitude of AX times I plus the magnitude of AY times J plus the magnitude of AZ plus K. So the overall magnitude of the vector A is just going to be the square root of those coefficients squared. AX squared plus AY squared plus AZ squared. So let's now go and pull off those components and look at our vector again with our Cartesian axis. And we can see that there's an angle between each of these coordinate systems. For example, the angle between the x-axis and our vector here is alpha. The angle between the y-axis and this we might call beta, and the angle between the z-axis and this we'll call gamma. And one way of looking at that is to think of the plane formed by, say, the y-axis and the a vector. So this would be the y-a plane. So it's at a weird angle here. It's canted at an angle, and that would so the angle we're talking about here when we talk about beta is this angle. And of course, the same thing is true if we make this and we go ahead and create the ZA plane and the XA plane. With in your XA plane, so we're going to have an angle alpha, and then in your ZA plane we have an angle gamma. So we can actually use some trigonometric functions to calculate what these angles are. So alpha is going to be equal to, if you look here, alpha, so this is adjacent over hypotenuse. You can string in a right triangle here. So this is going to be the arc cosine of AX over A, and this is the magnitude A. So it's really the magnitude of AX over A, and this is AX here. So it's the X component of A, and of course this is A. So the magnitude of this, divided by the magnitude of this equals cosine alpha. So alpha equals the inverse cosine of the magnitude of AX over A. And likewise, we can have beta equals the inverse cosine of actually, to make this a little easier to take, why don't I do an intermediate step here and just say the cosine of alpha equals the magnitude of the component of A in the x direction over the magnitude of A, and the cosine of beta equals. Okay, so then the cosine of beta equals the magnitude of AY over A, and the cosine of gamma equals the magnitude of AZ over A. And here, let me throw in AY up here. We didn't put it in. So AY looks like this. Okay, and then that leads to, we can just take the arc cosine of all these and find out our angles. Equals, like so. These cosines are referred to as the direction cosines. Okay, if we think of a unit vector in A's direction, so unit vector in A's direction, this is simply just going to be A, vector A over the magnitude of A, which I'm just going to write as A now. And that equals AX over AI plus AY over AJ plus AZ over AK. And again, this is just cosine of alpha I plus the cosine of beta J plus the cosine of gamma K. So that's a unit vector in the direction of A. And we know with a unit vector the magnitude of the unit vector equals 1. Well, since that's the case, then 1 is equal to, so we'd square each of these. Cosine squared of alpha, each of these components, plus cosine squared of beta plus cosine squared of gamma. And that's a relationship we can use to help save us some time. If you know one of these, or if you know two of these, you can always calculate the third one. Okay, next topic we're going to talk is the addition of vectors in space. So say you have two vectors, one heading off maybe in this direction, which we'll call, say, A, and then another heading off in this direction, B. And we want to add those in 3 space together. It's really quite easy. So A plus B equals our resultant, as usual. So A plus B equals R. What's going to happen is you can kind of draw a parallelogram here in space to see how that works. But to get this, to pull this off, all you have to do is sum the components along each axis. So sum the components in the x direction, sum the components in the y direction, sum components in the z direction. So in other words, for a force, the resultant force is just the sum of all forces, or the sum of all x component forces plus the sum of all y component forces of all the vectors plus the sum of all z component forces of the vectors. And I've kind of added some components here for this A force so you can see what I'm talking about. So you have a component in this direction for the x, a component in this direction for the z, and a component in this direction for the y.